First exponential model we're going to cover is your law of uninhibited growth or decay. You also see it referred to in your homework sometimes as exponential law, so they mean the exact same thing. And so here's our formula for it. We have A of t equals A naught E to the kt. So what does everything stand for? Your A of t is the amount at time t. Your A naught, or you can call A sub 0. A naught is your initial amount. K is your growth or decay rate, and you can tell which is which because growth will be K is greater than 0, so positive, and your decay is when your decay rate is when K is less than 0 or negative. Notice neither of these can equal 0, so it's either less than or greater than 0. And then time is your t. So pause that if you need a second to write that down, and then let's go to example 1. So example 1 says the size P of a certain insect population at time t in days obeys the law of uninhibited growth. P of t equals 500 e to the 0.02 t. So we have P is our population, and our time t is in days. So determine the number of insect at t equals 0 days. So you could plug in your 0 into here, and we would get 0 times 0.02 is 0. E to the 0, anything to the 0 power is 1, and 1 times 500 is 500. So the number of insects at t equals 0 days is 500 insects. But when we're at t equals 0, that's my initial population. And so this is just another way of asking for that initial amount. So you can either plug that in, or you can just see that that means the initial amount. So it's whatever's in front of that E. What is the growth rate of the insect population? So that is my K right here. Now, when it wants these in rates, it more than likely wants it as a percent. So you take that percent, you take that decimal and move it 2 times, and that's going to give me 2%. So what is the population after 10 days? Well, there's my T. So I need to find P of 10. So we have 500 is E to the 0.02 times 10. So calculator work here. And because we're talking about insects, we're going to round to the nearest whole number, nearest whole insect. So we have about 611 insects. D wants to know, when will the insect population reach 800? So far, this has been pretty straightforward. Now we got to do a little bit of work here. When will the population reach 800? We are talking about my function. When will it equal 800? So I would put 800 equals my function. And it wants to know when we are solving for our time here. So what are our steps for exponentials? We'll first isolate the exponential. So my exponential is this e to the 0.02 t. So I need to divide that 500 over. Now, because this comes to a nice clean decimal of 1.6, I can use that as a decimal. So we have 1.6 equals e to the 0.02 t. So now I have isolated my exponential. Step 2 is to rewrite. So base to the other side of the equals, my log with a base of e is a natural log. So I have natural log of 1.6, and that's going to equal my exponent of 0.02 t. And then my last step is to divide that over. So we're going to get t equals the natural log of 1.6 over 0.02. So this is my exact answer here, but that doesn't really help me figure out what does that equal, right? So let's plug that, or let's use our calculator and get a decimal equivalent. And we get about 23.5 days. Now, with these law of uninhabited growth and decay, when I have a growth, and I can tell this is a growth because my K here is positive, when it has a growth, it loves to know when will things double. So here, when will my population double? Well, if my initial amount was 500, I'm wanting to know when will my P of T equal 1,000. We're doing this process all over again. We're going to be doing the same process all lesson almost. So we have 1,000 equals 500 e to the 0.02 t. So do it again. Isolate your exponential by dividing over 500, and that's going to give me 2. When we are doubling, this should always equal 2 right here. So we have 2 equals e to the 0.02 t. Now rewrite this. Base to the other side of the equals means I have the natural log of 2 equals 0.02 t. It's going to equal that exponent. And then lastly, again, divide that 0.02 over. So I've got t equals the natural log of 2 over 0.02. That's my exact answer, but that doesn't give me an estimate. So let's do t equals the natural log of 2 divided by 0.02, about 34, we'll say 0.7 days. Okay, let's try one more example in this video. So the next page, example 2, we have iodine 131 is a radioactive material. And so this whole thing, iodine 131 is its name. So I'm not going to be using that 131 in my formula and in my process. Okay, that's just the name. So it's a radioactive material that decays according to the function A of t, where A naught is the initial amount present and A is the amount present at time t in days. So we're in t in days, and A is the amount present. So assume that the scientist has a sample of 100 grams of iodine 131. So this right here is my A naught. That's my initial amount right there. So what is the decay rate of iodine 131? So I'm going to take my K right here and rewrite it as a decimal. So move that decimal 2 places to the right. And we get negative 8.7%. Anytime it's decaying, it will have a negative right here. How much iodine 131 is left after 9 days? So there's my T. So I'm going to define A of 9. That equals my initial amount, this 100, e to the negative 0.087 times 9. So make sure you are doing this with me so that you know how to do it when it comes time to do it in your homework. You get about 45.7. And we're in unit of grams. When will 70 grams of iodine 131 be left? So this is my A of t. So I have 70 equals, and then the rest of my formula here, 100e, the negative 0.087t. It wants to know again when we're solving for time. So same steps every time. Isolate, divide your initial amount over. So 70 divided by 100 gives me a 0.7. I can use this as a decimal because it doesn't keep going. I couldn't use this as a decimal because I'm rounding off numbers, but this is just a nice clean 0.7. So 0.7 equals e to the negative 0.087t, and I'll rewrite it. Base to the other side of the equals, it gives me a natural log of 0.7 equals the exponent. And then last step is to divide that over. So I'm going to get t equals the natural log of 0.7 divided by negative 0.087. That's my exact. Put it in our calculator and get a decimal equivalent. So about 4.1 days. Okay, just like when I have a growth rate, it wants to know when will this double. When I have a decay rate, it wants to know the half-life. When is it going to reach half of this initial amount? So my half-life will mean that my A of t is going to equal 50. So I have 50 equals 100 e to the negative 0.078t. So solve for t. Same thing, whatever this initial amount is, divide it over, and we get 0.5. And this is always going to happen too. Every time I am doubling, this will equal a 2. When I'm finding half-life, this is going to equal a 0.5. Now rewrite it. Base to the other side of the equals means we have natural log of 0.5, and that's going to equal my exponent. And then divide that over, and we're going to get t equals the natural log of 0.5 divided by negative 0.087. So that's my exact, but that doesn't tell me time. I'm actually just going to come up here and edit this to a 0.5, and that's roughly 8 days would be fine. I'm going to go 7.97. My math lab will, of course, tell you how to round. So we're just kind of winging the rounding here. Before you go on to example 3, make sure you know how to do examples 1 and 2, because once we get to example 3, I don't have a formula anymore. I'm going to have to make this formula from the information that they give me. So make sure you know 1 and 2 so that you can move on pretty easily to example 3 and beyond.